Compound interest is basically when I start off with some amount of money, like say, let me zoom in a bit, say $1. Um, if I compound that, then I multiply this by some interest rate. So if it's 50%, then I can multiply that by 1.5, and then I get $1.50. And then I compound this again, then I multiply again by 50%, so 1.5, then I get 2.25, and I keep doing this. So this is basically the concept of compounding money. So what if I compound something continuously, or meaning I compound it at infinitely small increments of time? Because compound interest, you can compound something monthly, you can compound it yearly, you can compound it biannually. But what if I do it every split moment, like an infinitely small increment of time, so that at every constant moment that passes, I'm receiving a really, really small amount of money? So how exactly would I calculate that? So this standard formula for compound interest is A equals P times 1 plus R over N to the power of NT. Where R is my interest rate, P is the initial money I'm starting off with, N is how often I'm compounding it in a year, and T is how many years have passed before I take out the money and I end up with A. So if I want to compound this at infinitely small increments of time, then I want N to be as large as possible. So what I want here is basically the limit as N approaches infinity, because I want to compound it at infinite amounts of time, right? Infinitely many times. I want the limit of this. Okay, we can move P out because it's just a constant and it doesn't affect our limit, so we can just do P times the limit as N approaches infinity of 1 plus R over N to the power of NT. Okay, cool. So we have this formula. Let's take a moment here to stop and talk about the concept of E, because we can use that to kind of simplify this. So E is defined as the limit as N approaches infinity of 1 plus 1 over N to the power of N. So what does this mean exactly? This means that when I compound something at a rate of 100% at infinitely small increments of time, after 1 year, I will end up with E dollars. So this is pretty cool. And you can kind of see how that formula works if you look at this and you look at the standard formula. You can kind of compare the variables. So we can use E to kind of make a substitution here, and then we can kind of write this limit in terms of E. So how exactly should we do that? Well, notice that R over N, R is just a constant, right? So R doesn't affect the limit of 1 over N, because the limit of 1 over N is the same as the limit of R times 1 over N, because multiplying it won't really do anything. So let's say I have some number M, where M equals N over R, right? So as M approaches infinity, then N over R will also approach infinity. So I can kind of like substitute M for N over R in this limit. So if I do that, then I get P times the limit as N approaches infinity of 1 plus 1 over M. Let's see, can we write N in terms of M? Well, yeah, we can. So we have M equals MR, so we can do MRT. Cool. Okay. So now if you look at this and you look at E, then you can notice like the similarity, right? We have 1 plus 1 over N to the power of N, this limit, and we have 1 plus 1 over N to the power of N. So this is basically E, so we can just do P times E to the power of RT. And so that's it, we're done. That's our answer. So for continuous interest, if you want to calculate something where you're receiving money at every single possible passing moment at a fixed interest rate over a certain period of time, and you're starting off with P dollars, then you will end up with P times E to the power of RT dollars. So this is a pretty cool proof, and I thought it was really helpful for me, especially in Algebra 2, because our teachers just gave us this formula and they didn't really explain it. So I just thought I'd go over that, but I hope you found this video helpful.